So our next speaker is Dr. Paolo Guida. He's a research scientist at KAUST, where he also received his PhD in mechanical engineering recently. And he's also the CTO of the newly founded company Emerging Solution Technologies. And today's talk is about AI-driven chemical characterization with MolEvo.
So, good morning, everybody. Today I'm going to explain more or less what MolEvo is and what is the reason behind the creation of this software. So, first of all, I'll start with an overview. I'll proceed with objectives, so what we were looking for and what we created. Then I will explain briefly what evolutionary computation is, because it's still considered AI for some reason. And then I will show you some tests, some results that we got applying this to real industrial problems. And then I'll conclude with some remarks. So first of all, liquid fuels will be around for a lot of time. So this is a projection forecast from British Petroleum, I think, 2019. So they predict that liquid fuels are going to be 30% of the total energy consumption, because there is not just Europe in the world. And this is not even considering that biofuels are in the renewables. So there are going to be liquids also here. So all these fuels are increasingly complex for a simple reason, that half of what is produced in a refinery, more or less, is residue, and it's very heavy. Also, biofuels have the issue that they come from different sources every time. It depends what you use as a raw material. Therefore, they are also extremely complex. Now, how do we understand what we have in hands? So the normal process is you go to the lab, you take your sample, you go to the lab, you do all your analysis, FTICR, NMR, and so on. They are all partial, in the sense that sometimes, most of the times, you cannot dissolve all the sample. So you get an information which is not really quantitative, because it considers, let's say, 30, 40, 50, 60% of the sample. It takes a lot of time. It costs a lot of time, because those machines are very expensive. They break often, they often break. And also, you need to have scientists, which are extremely good, fantastic, but still, you need to pay them. Then you use some software to reconcile the data, but this does not always work very well, because this software are usually machine-specific, and therefore, if the information is partial coming out from the machine, it's partial also when the software processes it. And the results are unclear, because each machine gives you information. They are often on functional groups, and they're often non-comprehensive of everything. And as I was saying, it takes a lot of time. So what we try to do with MolEvo is the opposite. So basically, you take few data, and you use this data in order to constrain an eventual system of molecules, an eventual cluster of molecules. In 5 minutes, you get the results. So you get a usable surrogate. You can have also something more complicated that is not usable, but is informative on the structure of the fuel, of the liquid mixture, let's say, because sometimes it's not a fuel. Okay, so there are several use cases for this type of application. So you can do inline process quantity control. For example, imagine you're a refinery and you have to blend diesel and heavy fuel oil, for example. So a 0.1% less or more of diesel can make $1 million difference. Therefore, you want to know how much of each you need to put in order to meet some specific targets. Sometimes these targets are more complicated than just elemental composition, so they do not scale linearly. So it's convenient to have a prediction of what you're going to end up with. Same thing with other type of processes. So imagine you're producing a base oil. You need to have some an aromaticity, a specific aromaticity at the end of the process. You don't want to run a full test. So you take your density, you take your I don't know, TGA or distillation or the true boiling point characterization, and you process it with MolEvo and you get the results. Another is data-oriented decision making. So again, if you want to develop a new process and you want to know what to expect from this process or what type of decision you want to take, let's say close a machine, open another one, and so on, this can be useful. Another factor is process optimization, and of course this is straightforward. And the fourth one, which is probably more interesting for you, is modeling tools improvement. So there is a big an important point to make when talking about liquid fuels. They take a lot of time to evaporate, more time usually than the time that they take to react, in order to react. Therefore, you need to model well evaporation, you need to model well fluid dynamics, and both these things depend on the physical properties of the fuels, right? Because you need to have correct viscosity, correct density, and particular correct critical properties in order to predict how quickly they evaporate, what evaporates first, and so on. So after this, I will introduce more or less what evolutionary computation is. So evolutionary computation is based, of course, on the evolutionary theory. So you have a path that starts with the creation of a random pool of individuals. In my case, they are molecules. So you just randomly put together functional groups. Then you have a while, and actually the mutation struggle with the while again, but anyway, you have a stop criteria. So you start your loop, and you evaluate how this pool of molecules represent, how well this pool of molecules represent the system that you want. So the system that generates, for example, your density, your distillation curve, and so on. Eventually, you rank these molecules, these bunches, these ensembles of functional groups, and you say, okay, this one is more likely to exist, this one is less, and so on. Once you've ranked those molecules, those ensemble of functional groups, then you perform two operations. One is the crossover. So you take two of this arrays, because they are arrays of functional groups, and you merge them. So depending on how good they are, you merge them. Or you can have mutation. So you randomly change one of these functional groups. To do this, you need to have a representation of the molecule. So there are several ways to represent a molecule. The easiest and the most, and the one that was first implemented in MolEvo is just based on functional groups, following the definition of functional groups that was given by Nanolal. That is the guy that made the most comprehensive group contribution method so far. So you have, let's say, a CH3, CH2, CH, C, CH, aromatic, and so on. There are many more than this. I just kept it simple. And if you want to represent a molecule, then you have a simple array, so 2, 2, 0, 0, 0, which means that you have 2 CH3, 2 CH2, and you form butane. It's very, very, very basic. Now we are moving toward a different approach, which is a bit more complicated. So there are actually 3 degrees of complexity in the representation that we have adopted. So the first one is this, so only functional groups represented by an integer. Then now we have a series of integers plus some Boolean variables that tell us how the molecule is oriented and if it has particular characteristics. This helps us distinguish the type of molecules. And the next step is to use miles. So we are trying to use miles in order to replace this type of definition and be more, how to say, generic and much more accurate compared to what we have right now. Now the crossover, just to explain better what crossover is. So you have these 2 molecules that were randomly generated. Let's say we have this array of functional groups that they are arranged in this way. If you merge them, you end up with this. And this one eventually is better than what you had before. So this one fits better the constraints and the objective functions that you specified in your system. Another, the second step is the mutation. So mutation works more or less like this. So you have just a random addition or substitution of a functional group. It can be addition or substitution actually, because it's just changing a number in the array. And you end up with a different molecule. Now, you didn't have this molecule at the beginning. Now you generated something completely different. This is I want to stress the point that mutation is necessary in order to preserve the diversity in the system. Otherwise, you will end up having only paraffins because they usually approximate well every system. But since you want to preserve diversity, and since biofuels, for example, have a lot of oxygen, you need to enforce some random mutations sometimes. Also because if you consider that usually the amount of oxygen-containing functional groups is lower than the amount of the only carbon-containing functional groups, it's necessary to have a method path to include those, which are usually zeros. And then you have some structural constraints. So some structural constraints that have to be respected when you build a molecule. For example, this molecule does not make any sense because it has sulfur here and so on. So it doesn't have a feasible structure. But when we rank this molecule, it's going to score very low. If it scores very low, it's not included in the next generation. But that one, this will eventually evolve into this one when combining that. So we do not completely discard this molecule, but we use it for the next step because it may have some features that are useful in the next step. So I say it has some features that might be useful, but it's I'm combining them by hand, but it's actually an automated process. So you will end up having a very wide distribution of molecules at the end. And this is what happens. So basically, you start with this molecule. It has a certain fit. So let's say this has a certain critical temperature, critical volume, critical pressure, which are usually the variables that specify the thermodynamic state of a molecule. And it goes on into the next generation, maybe approximating better the ones that I've specified at the beginning. And again, generation by generation, we evolve, we change the structure of the molecule in order to get a better approximation of our objective. Now, there is another important point. So as I was saying before, that if you leave those molecules evolve by themselves without any other constraint, any other force on the system, you will end up having mostly paraffins. There is no doubt about that because they are usually in the best shape to have the right critical properties. Simply because they usually are the largest part of the fuels people have calibrated, of the mixtures people have calibrated the pseudo-components methods with. But in order to preserve the diversity again and have a reasonable and accurate surrogate, we need to include something that is crowding distance. So this is a concept that is common in evolutionary computations, but we've changed it a bit. Because the good thing of evolutionary computation is that it's meta-heuristic. You can really calibrate your model for your purposes. So it's not working anymore as a straightforward method for evolutionary algorithm, but it's working as MolEvo now. It's like we are considering the fact that you want to have diversity in the molecules, the molecular structure, and we preserve this diversity by applying the crowding distance concept. But the weights that we use in order to say this molecule is better than the other one are generally a function of the structure of the molecule. So let's say I have a sample that is very aromatic. Therefore, therefore benzenes, molecules with aromatic groups, are going to be favored over molecules with linear groups. This crowding distance concept just tells you, okay, these molecules are very far from this other molecule, therefore it's a good one. So I will rank this one very well because it's the only one representing this section of the system. While if I go in this area that is very crowded, I don't want to preserve all of them. I want to preserve just one of them. It's enough for my system. Okay, now this is the outcome that we have from running MolEvo. So as you can see, we not only have the critical properties of each species, and as you can see, the critical temperature, for example, is the same, molecular weight is the same, critical volume is the same, but the molecule is different. This is because the structure that we create is different. Also, we have a mass fraction specified for each molecule. So how do we specify a mass fraction while we are evolving a series of arrays? There are two steps in the computation of the surrogate. The first one is devoted to find molecules that specify a certain thermodynamic characteristic, which is the critical properties mainly. And the second step takes all these molecules and optimizes a variable, which is the mass fraction, in order to match bulk properties. The bulk properties can be whatever. It can be the density, it can be elemental composition, that's the best actually, but it's all parameters that are quick and easy to calculate. Now this is another example, the biofuel, as you can see here. We have this, that are the functional groups. You have OH, long, short, aromatic, aldehydes, esters, everything. And then you have the critical properties of each of them. Sorry, I forgot to tell you this. Yeah. So once you have the structure of the molecule and you have specified that, you can use something that is very useful again, which is the group contribution theory. If you go on the PERI, the Chemical Engineering Handbook, and you check what are the uncertainties of the functional groups calculations to predict physical properties, they are extremely low. I mean, they work very well. It's 3%, 5%, so it's good enough for any practical application. And also, the most important thing is that it gives you a physical properties that is actually a function of temperature, and it's actually a function of composition, which is extremely important because chemical systems evolve in time, so we cannot keep density, for example, constant in time. We cannot pretend that viscosity is constant in time. With this, or constant in time, change in temperature and composition. So this gives us more reliability, let's say, on how well properties are approximated. Okay, now another outcome is the biofuel, as I was mentioning before, and this is another interesting thing. So you can decide how complex your surrogate has to be. So if you want to have quick or simple models, you can just keep the number of molecules low, and you will have very short time to wait. It's going to be 10 seconds, 5 seconds, 3 seconds, depending on the type of system you would like to replicate. However, generally, if you keep the molecules below 18, it's going to work well enough for modeling purposes, also because you cannot consider more than that for most applications. But it's going to be less informative compared to the one when we consider 120, 140 molecules, which is more informative. It's going to tell you more or less what is the aromaticity of the sample and so on, all this nice information to have. But still it takes a lot of time. So depending on the scope you have, this is going to work differently. However, there is a point. There is a drawback in this. Sometimes you want to have a lot of molecules because the information you want is on the type of the type of fuel, but you don't have time. So if you want to do inline process monitoring, you have a densitometer, inline densimeter. You know more or less the boiling point of the system, and you read the sulfur content, let's say. So you have this three information. You want to have inline monitoring of your system. Unfortunately, you may need to have a lot of molecules, but this will take a lot of time. So for extremely fast processes, we really need to reduce the computational time. So this is something we'll work on later. Okay, now some applications. So this test case one. So this whole thing of MolEvo started thanks to Hendrik Müller, which is an Aramco engineer and scientist, because Hendrik is scientist, that proposed. So MolEvo was born in order just to address heavy fuel oil, because that was my PhD. Then Hendrik came and he said, okay, this is very interesting. So let's try that with other systems, other fuels. So what we tried to do basically is he provided us with some data, which were very, very extremely comprehensive on the structure of several refinery products. And I tried to run it. We tried to run them with MolEvo, and then we got the full characterization. So he used to give us only the density distillation curve, which is very good information, and the elemental composition, and then we tried to predict the structure. And actually, the results of Hendrik's data reconciliation, because he ran several analyses, and the results obtained by MolEvo were extremely similar, were extremely good. Sometimes when there was a lack of information on the experimental side, we could reconcile the data thanks to MolEvo, because, for example, you don't get the right elemental composition out of an FTICR analysis, but you could get it with MolEvo, because actually that was a constraint. This is S1 molecules. So this is molecules having an S1 group in them, and this is their size, the size in terms of aromatic rings. As you can see, the results are pretty good, are usable at least. I'll also considering that there is an experimental uncertainty in every type of simulation. Then there is another application that we had, which was with Lubref. So we have this ODS project. It's basically sulfur reduction using an oxidative desulfurization system. And we wanted to know if this is doable, if this is applicable to base oils. But we cannot know a priori, because ODS is strongly dependent on the structure of the molecules that make the base oil. And the base oils are pretty complex themselves. So what we did is basically run MolEvo on the few data that they provided us on these base oils. And then we found out that mostly the molecules that are in the base oils are thiophene molecules. Therefore, ODS would work potentially. And we went ahead and tested, and it actually works. So this is the type of applications that this software has. Another thing that we are trying to do right now actually is to have a surrogate for AP. There's a project at KAUST, so Elia is using MolEvo in order to understand if we can predict the SARA composition from MolEvo, and then use that with some modeling tools that were developed for this project. However, for example, for this from A products, we don't have distillation curve of all the fuels that they provided, or I don't have it at least. So we use the TGA. So there is a certain flexibility. Of course, the results are not going to be as good as with real distillation curve, but it's predictable, because then we can simulate the TGA and go back and iterate. So this is the way we ensure that the thermodynamic is consistent. Then the step which is actually in progress now is to have a software, because the main issue is that MolEvo was on a terminal since its beginning, and we never people in companies in industry do not like to have to use a terminal. I figured that out. And so they want a usable and user-friendly version of the software. So this is what we are trying to put together now. As you can see, I don't know if you can see it, but you can specify, let's say, density, the normal boiling point. You can actually tell the system what is the origin of the sample. So that helps a lot in the calculation, because, for example, if it comes from the refinery and it's been processed, it's going to have more olefins, for example, or not, and so on. You can use all the data from HNMR, CNMR, and so on, FTICRMS. All this data can be used in order to improve the prediction. You will input all your distillation curve or your TGA, and so on. And the system is going to calculate what is the most, the best surrogate, let's say, the best mixture for you. So I will try to conclude because it's taking too much time. So yeah, so this is the group that is working currently on MolEvo. They're all helping a lot with the development, and I'd like to thank Professor Roberts, of course, for the support, although it was not our primary focus for a lot of time. Yeah, with this, I think I'm out of time. There are some few more slides, but I will keep them for the questions. Thank you so much.
Questions for Paolo?
Thanks for the talk. This is really a question for clarification. Could you go back to slide 18 very quickly? I'd love to get more of an explanation about when you talked about molecular diversity and what that plot means. I think it was 18, yeah.
Yeah. So, sorry, what is the question again?
So you made some comments about molecular diversity and how important molecular diversity.
Molecular diversity. Sorry.
Yes, and if you could explain and expand on the understanding of this plot, please.
Yeah. So I will try to explain it this way because it's a bit complex. So imagine each of these dots have different molecular structures. In the sense, some of them are aromatics, some of them are naphthenes, some of them have sulfur, some of them are alcohols. So they are all different molecules. Now, if we do not preserve the diversity from generation to generation, so we want to have all this diversity, because eventually our system has all this type of molecules. However, if we leave the system free to run just with crossover, let's say we generate an array of molecules, we rank them, and we leave it free to evolve, we will end up having only paraffins, or mostly paraffins, so molecules that are linear with no other functional groups. Because in this space, so imagine this space, there's objective function 1, objective function 2. These are the critical temperature and critical pressure that I've specified. So I want to have that type of molecule with that thermodynamic, let's say, description. And I create molecules in order to match those objective functions. So imagine in this area here, where all these molecules are, because they are effectively molecules at a certain point, they are all paraffins, right? And this fit very well the system. So eventually I will end up having a generation which is mostly paraffins. But I don't want that. So therefore, what I do, I measure the distance between this and this, for example, and I say, okay, this one is here alone, so I don't have many of this. I need to preserve it. So it's just a preservation of diversity. Let's say this is an alcohol, and this is a cluster of paraffins. I like paraffins, but not that much. I want to preserve the alcohol. So I will rank this better, because there is more distance between this molecule and the rest of the molecules. So this is the idea. I don't know if that was...
Yeah, this was helpful. Thank you.
Okay, thank you.
Hey, Paolo, really interesting talk. If you go to the next slide, I was a little bit puzzled. So if I understand it correctly, what you're looking for is give me a molecule which has a certain critical property, right?
Yeah.
So that the critical properties are the input, is this correct?
No, not really. No. So the idea is, so as you can see here, for let's say these 4 molecules, the properties are all the same. Okay, because what I do at the beginning is to specify the critical properties. So I want to have, so basically, actually this was partially inspired of your work, from your work, 2018, I think, with the Govinda Raju. I don't know how to spell his name. However, so you take a distillation curve of a system, you break it, and you will have each of the points of the pseudo components specified by critical properties, eventually. And then you can do one thing, which is very simple. You take this, you try to reconstruct this distillation curve, and then you adapt until you match the initial distillation curve. You will end up having an array of pseudo components, each one specified by these critical properties. These critical properties eventually become part of my objective functions. So I build the molecules just based on these critical properties, on these objective functions. Now, once I've built this molecules based on the objective functions, then what I can do is to do my evolution thing, and I will end up having a structure for this, a phase for these molecules. So they will be fully specified with their functional groups. Once I have the full structure of the molecule, I can just use the group contribution theory from Nanolal or whoever else. Nanolal works much better than the others for most properties, and I will have all the physical properties.
I think the specific question I have is your critical temperature and pressure, they look unphysical. So is this 30,000 Kelvin?
Probably it's a miss. Yeah, no, this is an error. This is just a mistake.
Okay.
Yeah, because
so
I did it there. Yeah, sorry. I copied from an Excel sheet and without copy the value.
Okay.
Sorry. Yeah, that doesn't make sense. Okay. Sorry. Just also because there is a 0 at critical pressure. Sorry. Yeah.
I think we need to move on, so thank you, Paolo, again.
Thank you.